Good afternoon, everyone. Welcome to Tech Talk on KMIT platform. Today's topic is the potential of artificial intelligence in nuclear power plant. This talk is presented by Dr. Ahmed Rashdan. He's working as a senior R&D scientist at Idaho National Lab. He holds a PhD in nuclear engineering from Texas A&M University and has more than 15 years of experience in industrial and research focused on automation, instrumentation, and control. And he has worked with, he's currently working with INL, and he has also worked with ABB, Texas A&M, International Atomic Energy Agency, and many other organizations. His experience includes automated work process using AI methods and advanced analytics, online condition monitoring of nuclear systems, control system design and development, anomaly detection, and automated mission modeling and simulation. Dr. Rajnan has contributed to a lot of scientific papers and DOE events. He has authored more than 50 technical reports and journal papers and six patent applications. He's an active reviewer of several nuclear energy and IEEE journals, as well as many DOE grants. Dr. Rajdan is a senior member of IEEE and a member of American Nuclear Society. Please join in welcoming Dr. Rajdan, who will be providing a tech talk on AI in nuclear power plant. Dr. Rajdan.
Thank you. I'll go ahead and share my screen. There you go. Thank you, Himanshu, for the introduction, and thank you, Walter, and everyone for the invitation. So as Himanshu mentioned, the topic of the presentation today is the potential of artificial intelligence in the nuclear power industry. Now, to start with, I have a disclaimer, which is, of course, this is going to show up in the wrong time. So I have a disclaimer, which is that I wasn't sure how knowledgeable the audience is going to be with regards to the topic of artificial intelligence. So what I focused on in this presentation is to give you a broad idea of the different topics we're tackling by leveraging AI, artificial intelligence, or AI. But you won't see the level of details that you would typically see in a journal paper, because this is not really dedicated in a certain topic where we go in depth. I'll touch briefly on some technical aspects of the projects, give you an idea of everything we're doing, I should say everything I am doing. There's a lot more going on at INL and within the programs I'm going to mention today. And if you are interested in any more details, please reach out to me. I'll show you my email at the end. And it's there in the slides. So if you have any more questions, you can ask them today, or you can reach out to me by email, and I would be happy to answer them. So to start with, I'd like to acknowledge the funding sources for the majority of the work I'm going to present today, which is the Department of Energy Light Water Reactor Sustainability Program, and the Office of Technology Transition, which is through the Technology Commercialization Funds. And from an organization point of view, I'd like to also acknowledge 3 universities. FIU is the lead one. I'll come back to it in a minute. University of Idaho and Purdue University too. So I'm showing you here a list of names from Idaho National Laboratory, and actually the first 4 names are FIU students that we hired as interns over the past few years. And we had an amazing experience. We were very, very impressed with the quality of the students from FIU. And we still have Roger Boza as an active intern for the past 3 years now, almost 3 years. Cesar Reyes just joined us recently and still working with us. Michael, I think he left and he's working for the industry now, and Christian Dow is still a student. So we've been working very closely with FIU, and a lot of the efforts I'm going to discuss today has been achieved because of the students that helped us get there. And actually, I would forward a lot of the questions I will get today to Roger Boza from FIU, because he's very, very active or involved in many of these projects. So to start with, looking at the mission of how to use AI in the context of nuclear power plants. I'm showing you to the left a typical control room that is in a US nuclear power plant. And as you can see, it's very manual. It's very analog too. It goes back to the maybe 80s in terms of technology. So there is it hasn't been automated much since then, and there are multiple reasons on why it didn't get the automation like other industries did. And to the right, I'm showing you a cockpit of a modern airplane, and you can see it's very modern. You only need 2 people to operate the airplane. You can actually even go into autopilot, and things with the airplane would fly by itself. So the question we had is, how do we transform our industry from the model that we have to the left to something similar to the one we have in the right? Excuse me. And that's the mission of the Light Water Reactor Sustainability Program. So the program is aimed to improve the economics and reliability of the plants while sustaining the safety. And we are researching and developing means to get there. And hope for this means to be picked up by the industry. And we are actually working with the industry, very closely with the industry, for them to adopt these technologies and transform their model of operations and maintenance. Now, within that transform arrow I'm showing in the middle, there are multiple key technologies that we leverage, and AI is one of these key technologies. And what I'm gonna do today is describe to you some of the examples of how we're using AI to automate some of the activities in a nuclear power plant. So the first set of example, or the first application or set of applications, is condition monitoring. And when you talk about condition monitoring, it basically means you're trying to determine how much time or how much lead time do you have for an equipment to operate normally before it fails. Now, everything in time is going to age, and every equipment you have in the plant is going to, at some point, require some sort of maintenance in order for it to be operable. And the key question is, how long do you have? In terms of the model that we have at the moment in the plants, if you look at the failure, and this is your timeline to failure, usually right before the failure, you would have some sort of alarms. And usually operators get these alarms and they act on them. But on the other end, you would have the maintenance activities that are not based on any observed issues with the equipment, but you're predicting that based on historical data that you saw from this equipment and other equipment, that this is how much time you would have for this equipment before it fails. So you need to do some maintenance before that. Now, what we're doing is we're researching into all these different aspects of condition monitoring. And specifically, I have been mostly interested in anomaly detection. Now, anomaly detection is an area that fails right before alarms, but after predictive maintenance. And it's a function that's currently performed by operators. So instead of just looking at alarms and determining what's going on in the plant, you could actually start finding anomalies in the processes of the plant that might not raise an alarm yet, but that will raise an alarm at some point, and rectify them before they do. And I'll show you an example today in this presentation. And this example is actually from a nuclear power plant. So this nuclear power plant had a fan. It's called the drywall cooling fan. And this is here the drywall. And these are the fans here at the bottom. And what happened is that they installed this fan, and I think it was only a couple of years old. And they had 4 of them. And one of them failed on May 11th, 2018. Now that fan is relatively new, so it wasn't expected to fail. They didn't have any monitoring system on top of the fan, like sensors for vibration and temperature, so they couldn't really see this coming. But the problem is that within a couple of weeks, another fan failed. And when the other one failed, now you have 2 out of 4 out. They had to shut down the nuclear power plant. That took them into an outage for 6 days, and that 6 days outage, of course, costed millions of dollars. So that got them thinking: how could we see this coming? This is not something they don't want to see again happening, and they can't really install anything on the fans because these fans, they just didn't install any sensors on them in the first place, and they are in a highly radioactive environment. It's not easy for them just to go in and put some sensors on them. However, they do have sensors in the surrounding environment. So all these red dots I'm showing here are sensors that are for temperature. Some are for water flow, which is here. So in theory, they asked us, could we, using these sensors, infer the condition of these fans? And the hypothesis we tested it was, well, if the fan is degrading, then the temperature profile is going to get impacted because the cooling is not going to be as efficient, and then you might see some rise in your temperatures. And that's the hypothesis we tested. So just to give you on a high level what we did, again, this is not meant to be a technical presentation, so this is all just high level description of the methods that we looked at. So clustering was one way we looked at solving this problem, with the assumption that most of your data points or measurements for these sensors, if we convert them into a two-dimensional layout like the one I'm showing here, they should fall in two different clusters. One is for normal and the other one is for abnormal. So, or maybe you can actually put them in one cluster where you say this cluster is normal and anything outside that cluster is abnormal. Or you can have them even in multiple clusters where you can say, like I'm showing here to the right, where you have 5 clusters, and you can say 4 of these clusters are different states of the fan, and one is the abnormal state. So when we tested this, it didn't really go very well. I mean, I'm showing you here the dots in red and blue, with blue showing normal and red showing abnormal. And you can see there's a lot of false positives overall. I think in this case, our assumption was that state 2 is the abnormal state. So we do see an abnormal here. Oh, no, actually, I can't even tell, because if you look at it, there are here. So it just didn't go well. And we just discarded this approach. We tried the clustering approach. It didn't work very well for us. So we went into isolation forest, which is a decision tree. And the concept of this process or algorithm is simple. It goes again to the idea of cluster. So if I have a cluster of points like this, and I'm saying anything that falls away, just like this point here, for example, is an anomaly, and anything that falls inside it is normal. What isolation forest does is it randomly splits this cluster into segments, horizontal and vertical, by horizontal and vertical lines, and then based on how many segments you need to get to that point, it determines whether this point is normal or abnormal. Let me explain more. So if I have x1 here and it's normal and it falls in the middle of the cluster, and I tell you randomly just draw lines, horizontal and vertical, and every time you draw a line, you just check whether you're upwards or downwards from that line, or left or right. It will take you a lot of lines to get to that point because it's right in the middle of the mess of the whole data points. Well, when it's an anomaly, it won't take you as much. And you can see there's one line here, a couple of lines here, and we get to the anomaly. So that's kind of the basic concept of the isolation forest. It's that anomalies are usually have a shorter path to get to. When we applied this, we also got many anomalies in the process, and a lot of false positives. Was not a good thing. So again, a false positive, if you have a lot of false positives in your process, you end up spending a lot of time dealing with the false positives, to the point where the anomaly detection process doesn't make economic feasibility. So you need something that works really well in order for it to be deployable. So what we did next is we looked at neural networks, and we looked at LSTM specifically. And the idea here is that we go through 2 stages. First, we do a prediction. So we want to predict what the values are going to be, and then convert them to the actual values and generate some residuals. Now, I didn't mention this earlier, but there are the 2 fans that failed were FCU D and A. And I'm showing you here how D got detected, where we saw some sort of anomaly happening here. And the next question was for us, well, how do we decide that this is actually an anomaly versus this or any other deviation? What is a significant deviation for us to classify this as an anomaly? And I'll come to that in a minute. But I'm showing you here also in the process, we were not really targeting B, because B was just normal, but we could actually, as part of the process, identify another anomaly. And when we went and checked what happened there was actually a sensor failure. Using this LSTM, we could catch the FCUD failure 8 days ahead of time, and the sensor failures 2 days ahead of time. Now, you might think that's not really a lot of time if a week of time to know that you're gonna go into an outage in a week ahead of time, it's gonna probably help you avoid that outage in some form, because if you prepare for it, you might not have to do it. Now, this is the prediction and creating the residual parts. Now, once we have the residuals, the next question is, how do we build the classifier to decide that this is an anomaly or not? So in this case, we built we actually tried multiple different approaches. And one of the approaches was to conduct an F-test using the variance of the residuals. So what we did is we compared the residuals occurring in a normal window versus the residuals occurring in an abnormal window. And what we found out is that then when we have an anomaly, usually this ratio, the F ratio I'm showing here, gets basically significantly higher than when there is no anomaly. And of course, there's a journal paper coming out on this. So, and of course, I can give you more details if you're interested. It's just given the time I have, I cannot go deeper into how do we build this classifier. Going again to the results side of things, so you can see here, window 1 is the mechanical failure, showing up way more than other states of the process. And in this case, in FCUD, so we could actually see the failure here. And the other one that failed, the failure is actually these small bars. And we can actually see that the change of state of the reactor going into reduced power. So in this point, at some point of time, they went from 100% power, I think, to 85% or 80 something percent. That caused a big spike in the process, because it hasn't seen this before. So for it considered this as a huge anomaly. In reality, it's not. It's just a change of operating states. Now, of course, this helped us identify some other modifications we need to do to incorporate into this, such as including transients onto our anomaly detection process. And these are some of the efforts we're looking at the moment. Another aspect of this anomaly detection that we've just looked at recently is, when things fail in the plant, you gain some knowledge. So if you have these fans I just described to you, they just experienced a failure, and that's an information that you can use to improve your training process. The problem is that when you're trying to label some of your failures, you're not going to end up with a complete set of labels. So most of the time, you do not know that this equipment is actually in a full normal state, or it does have some issue that's undetectable and it's growing, but is there. So most of your data is actually unlabeled, but you do have some cases where your data is labeled because you did observe some failures. And that's why we had to look into semi-supervised machine learning methods. And in our case, these labels came from something that is called condition reports. And I'll come to that today in my presentation. I'll talk about these more details because there's much more research going into these. But condition reports are just documents that report status of equipment. So sometimes they do mention that there is an issue with this equipment and it needs some maintenance. So that gives you a label. And now you have to define a window of time around this label that you would apply to the data. So that's an effort that we started last year. And we have already, we've tested one of the methods that exists in literature. I think it's called DeepSAD. And we also developed our own. And there's actually a report published on this. But that's another direction that we also looked into. Okay, so now moving away from condition monitoring to a different topic, which is work process improvement. I'm showing you here to the right a figure of a typical condition report analysis process. So let me go back to what is a condition report and describe to you why we're doing this and how it's important. So in a nuclear power plant, everything that fails or any issue you observe in a plant, you can actually log this in a system. So this could be as simple as just a broken share that you noticed, or it could be something more severe, like an equipment, for example, vibrating or making some noise. You go into a system, you log this, you say, I will observe this in this location, and this is what's going on. And I'm showing you here an example. Some water was found on the ground, close, blah, blah, blah. And it seems like a flange is leaking. That's a condition report. Now that goes into a committee that gets to review this. And then it gets multiple there are multiple meetings that occur with regards to each condition report. Actually, I shouldn't see it. They don't deal with one each at a time. They actually deal with whatever they have at that day. All of them, they go through them all and review them and analyze them and make decisions based on them. But what happened is that this is usually this process that goes in here, the review, classify, and assign, sometimes happens multiple times. And think about the amount of condition reports that are created every day in a plant. This is really a continuous process, and it's very time consuming, very manual. Now, what we are doing now is building machine learning intelligence to do that. So a lot of these decisions are based on text, and some of them are based on some fields that are filled in categorically. And we can build a machine learning algorithm to replicate that process that is based on natural language processing with some machine learning, I should say. So this process is like whether this condition report is safety related, what kind of priority I should assign it, what kind of keyword it should take, and who should work on this. All these decisions can be automated. And that's what we've been working on. And we have something called Miracle that's also been developed by INL for that specific purpose. But automating this process gives us a lot of insight. I just mentioned to you with the anomaly detection that the keyword part, we can actually create labels that can be used for equipment reliability. And that's one application. But there are other applications that we are looking into in addition to saving time and cost. So this whole committee review process can be automated, as I mentioned, but there are multiple also benefits to that. But before I dig into that, you might just ask, what are we doing here? Again, in a high level, we're taking all the fields, the categorical fields and the text fields here. We feed them into a feature extraction engine, the text part of this, and then we build classifiers based on these. And we usually for the feature extraction engines, we use models that are commonly used. Facebook and Google has some like BERT or Roberta, if you're familiar with them. And the idea here is just to build classifiers on top of that. Now, a broader benefit for this effort that I just showed you is inspection or assessment of plants. So nuclear power plants are highly regulated. Just checking how I'm doing on time, which means that they have periodic assessments by the government, meaning the Nuclear Regulatory Commission, or they actually I should say inspections, or they have assessments of sometimes independent parties that that the industry has formed like INPO. And the aim for these inspections or assessments is to make sure that the plant is complying with the commitments it made in terms of its safety assurance, and they occur very frequently. And they are time consuming. They do require a lot of time from the plant and also from the inspectors or assessment folks. So it is a lengthy process that requires a lot of data gathering and data analysis. So we've been the reason we've looked at into the condition reports or the whole program that the condition reports is part of is to try to assess these activities too. And I'm showing you here. Oops. I'm showing here one example. So if you look at the inspection procedure, which is what usually is used when you are conducting an inspection, this procedure is usually based on something that is called plant risk model. So everything in a nuclear power plant has some risk associated with it, and that risk is usually the risk of it failing, and then that cascades into the whole plant risk, and that feeds into the inspection procedure. And this procedure, as I mentioned, this happens, they have dedicated procedures for different aspects of the plant. So it's not really one procedure for everything. And it audits the plant processes, including what I just described to you. This condition report process that I was just showing you here is actually called, it's part of a corrective action program. Corrective action meaning that you're correcting something that is an issue in the plant, you're taking an action to fix it. So if we can automate this process, one of the benefits of doing this is we can extract keywords from this condition reports. So let's say let's say you're interested in knowing whether something simple like housekeeping is becoming an issue in your plant. So people are becoming more sloppy, and you start seeing more keywords appearing as related to housekeeping. Now, that's usually if you start looking at how the counts of occurrences of housekeeping issues as an example over time, you can build a trend, and you can see if the plant is actually starting to have an issue with housekeeping as an example, and then you can inform the plant that you need to work on your housekeeping compliance. It's not going really well. Actually, housekeeping, I don't think it's compliant, but it's part of the compliance, but it does impact compliance. So the whole process of trending any issues in the plant would give a lot of insight to the inspection process. So now if you start seeing a certain pattern going upwards and downwards, the upward ones you might want to rectify, the downwards what we would want to also observe and acknowledge because it's a good performance, a good behavior. That whole process would be only possible by automation. And the reason I'm saying it's only possible by automation is if you have people randomly assigning keywords to these documents, it's not really systematic. It's usually inconsistent. People use their own words. The trending process becomes way harder. What we're doing now is we're creating an industry-wide keyword list that is driven by the data itself, and using that industry-wide keyword list as the only list that you can use from or select from when you create a condition report, that will allow us to create really meaningful trends. And that's another application of where AI is helping us. All right, so when I showed you this picture earlier with the multiple plants sending data into one location, one data portal here, one of the key aspects of this is integrating data from multiple plants. So we had to look at this, and that's a common problem with machine learning or AI. So if you're trying to build a classifier for a certain nuclear power plant, and then another plant comes in with their data, and you're trying to apply the same classifier to that plant, you'll have to do a lot of mapping because you built that classifier to work with the data from the first plant, and the fields coming in from the data set that you have from the second plant is not going to be the same. They use different terminology. They have different fields. Even though it's the same process, every plant can have their own unique way of applying that process. They don't have to have the exact same one. So one way to do it is the manual mapping process approach. So you basically have the classifier that you built for the first plant as an example, and you start mapping the second one to the first one. It's time consuming. You'll do mistakes for sure, and you might have to even discard some of the fields because they might not map to anything in the first plant. Another approach to do this is you combine all the fields in one single large field. So all the headers or all the columns you have in your data set, you just combine them all in one input, and then you build a classifier based on that input if you're building a classifier. And that's another approach we tested, which is called the adaptable data mapping approach. A third approach that we looked into when we are integrating data is creating a dictionary. So we use the data from the different plants to create a generic feature extraction engine, and then every plant can build their own classifier on top of that. Of course, you might ask why do I need to integrate data from multiple plants? There are multiple benefits from that. Mainly, you can design models that are much more powerful. We all know there's always an assumption that adding more data and the more data you have, and the more diverse your data is, the better in terms of the accuracy and robustness of your model. And we've actually tested this, and I'll show you some results now in a minute. But also, there are many aspects associated with risk and performance and feedback. And one thing that the nuclear industry has and it's unique to the nuclear industry, is the fact that it's a very collaborative industry. So they actually like to work with each other and help each other improve. So building solutions for the industry rather for a specific utility has a lot of value. Now I'm showing you here what we did when we actually combined two data sets from two different utilities. So if I have the data set from utility one and I build a model for it specifically, and this specific classifier, which doesn't matter. I mean, it doesn't matter what the classifier is, because in this case, we're building multiple ones, but we got an accuracy of 90%. When we did the same, when we used the same approach, but used the data set from utility 2 and built a dedicated model for them, we got 84%. So what we did then is we applied the model from utility 1 to the data from utility 2, and you can see we got 75%, and we did the other way around. So we applied the model developed using one data set on a data set that it hasn't seen before, and you can see the results were not very. I mean, they dropped. They were still better than our baseline, which is just guessing if it's a 1 on the classifier, if it's a 1 or 0. But in this case, it's not perfect. So what we did next is we combined the two data sets into one data set, and we built a model for the whole data set and then applied it to each data set separately. So again, I'll repeat that slower. We took the data sets from the two utilities, we put them into one data set, and we built a model for it, and we called it the combined model. And this is all using the manual approach. So we created one model using the whole, the whole data set from the two utilities, and then we started applying this to each. So we applied to the utility 1 and utility 2, and what we got is actually a slight improvement. This is actually 90, both of them are 90, but this is actually a bit higher in reality. There's some decimals that we omitted here. And in this regard, we got 85 versus 84. So a slight improvement. But that gives us hope, because we're adding data from different utilities does improve performance. And the hypothesis that we made with this regard is, or that was tested with this was important, because if you have data that is contradictory, so if you adding more data doesn't necessarily always help you get better models. If the data is doing exactly the opposite of what your model is trying to do, then it's gonna actually confuse your model. So we wanted this test to assure that this is actually the case. Now I'm showing you here that what we're using the adaptable model, this approach here, the results we actually got even better results. We got 92% and 86 versus 84 and 90. So we were amazed with the fact that even though this approach is actually makes things way easier for us, because now we don't have to map things manually, we are combining everything in one field and feeding it in, it actually got us better results. And also we're looking now at the dictionary, building a dictionary, as I mentioned earlier, but I'm not showing it here again because of time. So I'm just going to skip to the next topic. Another topic we looked into is inventory management. So in a typical nuclear power plant, you have an excess of $100 million worth of stocking of inventory in your warehouses. And the reason the industry does that is that because they have a conservative minimum stocking requirement threshold usually set. So usually you're safer to have things in stocked more than what you need than you are to require that part and find out that you don't have it and you have to wait for it. So that's kind of the approach that the industry has been taking. And what AI can do in this case, it can actually optimize that usage of that minimum stocking requirement number, that threshold that they currently use can be informed by the amount of work that you actually do. So if you know how much work you do, and you can, if you can predict how much work you will need to do, you can probably better optimize what parts you need and when you need them. And that would save you a lot of money. And we expect actually to save tens of millions of dollars for each plant using this approach. Now, when we started looking at this a couple of years ago, the first hurdle we faced was that a lot of the records they had in their inventory were duplicates. So you would have the same item created multiple times in their inventory. Every time they they buy that item, they might not just go and find that item and increase the quantities that they have of it. Sometimes they go and create a new entry, and that to create a prediction algorithm, because now you don't really know what the actual inventory that you have of that item unless you find out these duplicates and you consolidate them. And that's what we did. And in this typical plant, in one plant, we looked at the data set that has one unique record versus the one that have two duplicates or three duplicates or four. And you can see there are many that had duplicates. And actually, if you add all these together, you have actually more duplicates than you have as of single items. So there's a lot of value in doing in consolidating these records, and that's what we started with, and this is an ongoing effort. All right, so I'm moving now to a different topic, which is support functions. And specifically, I think I have 10 minutes left, so I'm gonna rush a bit. Specifically, we have the first activity I'm gonna talk about is fire watch. So in a nuclear power plant, you have sometimes activities that involve some fire hazard. So let's say you're doing welding and you think that's a fire hazard and you need someone, you need this to be monitored. What the plants usually are required to do is to have someone that is called fire watch to basically sit there and watch for a fire. And in case there is a fire, they report it, or sometimes they actually take an action. They try to put it off. Another case, which is where when their fire protection system is down. If their fire protection system is down for maintenance or because of a failure, then they are required also to have fire watch or watches in multiple locations in the plant. And this can become really expensive for a plant. And actually, this number here, $1 million per month, is something we heard from multiple utilities. So this cost can become significant. Now, if you would say, well, why don't I just put a camera and have someone build an algorithm that can do exactly what they're doing? And that's actually what we did. We developed a computer vision machine learning algorithm that can detect fires in videos, and I'll show you examples in a minute. The problem is that false positives. False positive with this is representative of basically people being called in or maybe calling in the fire department. You want to reduce the false positives as much as possible. So one thing I learned working with artificial intelligence is building a model to solve a problem is really the easy part. And of course, there are other easy parts, but to try to optimize your performance of the model to get the performance you need is where the challenge is. So in our case, we ended up having 16 different models being evaluated. And actually, at the end, we built an ensemble of these models to get the accuracy that we want, which is more than 99%. And that wasn't enough. We actually now decided to fuse other sensors in addition to the camera and the video. So something like smoke detectors or acoustic sensors to get even more accuracy, because we want to make sure if we say there is fire, there is fire. We want to reduce the false positives almost to zero. We're also looking at ways to detect smoke. And smoke is more challenging because you have steam, leaks, you have fog, mist. All these they resemble the shape of smoke. So building a classifier just to recognize the shape or the look, the shape of smoke or the looks of a smoke is not going to be enough. We're looking now at using temporal effects, the motion of smoke to maybe distinguish the smoke from steam and others. And if not, we'll still have to figure out a way to do it because it's really also valuable. Okay, so if you want to know what we did in a bit more details, so when I mentioned the 16 different models, I'm showing you here one of them. The data set we captured videos from YouTube, from Google, and Yahoo, thousands, or maybe I should say tens of thousands of videos and pictures of fire, and then we just built these classifiers using the different model architectures. Oh, when I say 16 models, I mean 16 model architectures. I mean, I'm assuming that's trivial, but just in case. So this is here one of them that we used. Again, just as an example, and there will be also a paper coming out on this, a journal paper on that. I'm showing here an example of the results we got. So you can see the thing I like about this video is the fire is on and off, and you can see it, you can track it as it goes down. You can see the accuracy going down. There you go, no fire, and it comes back up. It's fire, no fire. Just a small demonstration of how the algorithm is working. Oops. Okay. So one of the challenges we faced when we were applying this is sometimes we saw the algorithm is actually classifying fire, and we couldn't really understand why it's saying this is fire or not fire. And one good example is a lot of the videos we had firemen in them. So you had firemen next to them. And then when we started seeing when there was a fireman in the video without fire, the algorithm would get tricked into saying this is fire too, because it's learning the fireman as a feature of fire, which is of course wrong. So we decided that we need to create some form of transparency to know what the algorithm is actually looking at. And we used an algorithm that already exists. I think it's called GradCam, but I'm not sure. I'm using memory here. And it can actually provide you with a heat map of what is the driver for that decision when it set fire. And in this case, for example, you can see that the heat map is pointing around this area, which is the area where the fire is. So it is actually correctly classifying the fire for the right reasons. In other reasons, you would see that this is actually pointing at things that look like fire that are not fire. And even though you had fire in that video and the classification decision was correct, that there is fire, it wasn't doing it for the right reasons, which is also something we want to look into. I have 6 minutes left, so I'm gonna go faster a bit. Another application is gauge reading. So a lot of the nuclear power plants being, as I mentioned, a bit outdated and not going through a lot of modernization efforts up until recently. They rely a lot on analog gauges, like the ones I'm showing you here. And the problem with that is they need to log these gauges on a regular basis. So the process itself is very manual. It's expensive. I mean, it takes a lot of time, and it's also prone to human error. They have people walking around just to basically collect information at least once a day, if not twice, and so on. So what we also did is created an algorithm or a software or a method, I should say, and a software to read gauges at oblique angles. Now, the oblique angles part is the tricky part because you'll find solutions out there that can read gauges. Actually, now you can buy devices that can fit on a gauge and it can read the gauge for you and digitize it. But when we look at the panel like this, you have multiple gauges. Some of the panels actually have tens of gauges in them. It just makes more sense to have a camera installed on the wall or on a tripod or with someone and take a picture of this whole panel and the gauges get locked. Now, the challenge is these gauges are not going to be facing the camera perfectly. So they will be tilted by a certain angle. And the algorithm we created is basically focused on how to read these gauges despite these angles. So an example here. So if you're looking at this panel here and ask you to read it, we're actually we're showing you here this same panel, but it's unskewed, and you can actually now see the bars or the needles, sorry, on the scale, and you can, to some extent, if you know what the scale is, you can read it. If I give you this picture here, you won't be able to read it, and that's basically what we're doing with the artificial intelligence. We're rectifying the images and actually then reading them and logging them into a database. Now, taking a picture of this whole panel at once and just logging it is going to be a matter of milliseconds rather than the time it takes him now to do it. And of course, there's also potential to other activities, like in some cases, some of these gauges, when they get logged, the plant is required to have someone else go in and log them too, because they are really critical and they want 2 different people to do it. So now we can use something like this tablet to do that instead of having to ask someone else to come in and do the exact same thing. I think this is the last application I'm going to talk about today is, and it's in my view, one of the coolest. So we're also flying drones autonomously in a nuclear power plant. And the reason we're doing this is there are a lot of activities in a nuclear power plant that rely on people walking around and collecting data. And this could be just as simple as a security round, just to check that everything is in order. It could be an operator round to check that equipments are okay and running just fine. Could be inspections. In some cases, you want to access hazardous location. You don't want to send people in. You want to conduct radiation surveys or warehouse surveys and so on. There are many, many applications for drones in a nuclear power plant. Now, the challenge is most of the nuclear power plants environment is indoors, so there is no GPS, and you have doors between these indoors environments. So having something or a drone that flies based using LiDAR or some other technology, now you have to have one in each single environment. That can become really expensive very quickly. And then, of course, the battery capacity of these drones, they can only fly for a shorter period of time before they need to be recharged. So what we looked into is we wanted something cheap because we wanted to deploy as many as possible within these door isolated environments. And we wanted something also that is accurate, that can allow the drone to fly autonomously, accurately within these environments. So we created drones, which is the name of the technology. And I'm going to play this video and then I'll tell you more about it.
There's no sound, Dr.
Oh,
Rashan.
there is no sound. Okay, I thought we resolved this. Apparently, sorry about that. Okay, so I could actually replay it, but what I would do is I'm gonna share the link with everyone on the chat afterwards, and you guys can play it. It's available on YouTube. Actually, if you type this on YouTube, you'll find the video. The basic concept, because if you're out of time, otherwise I would have replayed it. Okay, so the basic concept of this is we use inserted visual features, and we insert these features to be easily detectable. And in a specific, we're using QR codes, just like the ones we're showing you here. So you can actually print QR codes on A4 paper and deploy it along the path of the drone, just like I'm showing in this picture here. And what the drone is going to do is, when it's looking at that QR code, in addition to just reading it, it can actually look at the view of it. So if you're looking at the QR code from an angle, you will see something like this trapezoid. You won't see a square anymore. You'll see like a trapezoid. And rectifying that trapezoid to a square, or a rectangle, depends on the shape of the QR code, is actually going to give you an insight about where the drone is with respect to the QR code, provided that you know the size of the QR code. That's kind of on a high level the concept of how this works. So with this, if you find the location of the drone with respect to the QR code, all you need to do is just feed it back into where you want to be, and you can have an autonomous driving drone. So ideally, we would fit this along the route of the drone, and then the drone is just looking for the QR codes as it flies, and we could achieve an accuracy of in the order of a few inches. Now, whereas the AI process, the AI in this is finding the QR codes within that environment, and then to be able to calculate the exact location with respect to them. That's where the AI kicks in. All right, this is this one doesn't have audio in the first place. So we because of Corona, we couldn't fly this at the lab. So we actually simulated this in a real environment, in a simulated environment, using the real algorithms. And as you can see here, this is the drone from the top view, and this is the front view of the drone. You can see it flying. I don't know if it's very visible. It's really small, but you can see it's actually reading finding the QR code in every frame, and then drawing a box around it, and from that box calculating where the location of the drone is to a high accuracy. And in this case, now it's going to land on the charging pad, and we can control how accurate we want it to be. And there you go. And I think with that, I'm out of time. I'm actually 1 minute beyond the planned time, and I think I'm done. I don't know what's going on. There you go. Questions?
Well, thank you, Dr. Rashan. Thank you for your time. We do have some time if you want to go back and play the video. Remember, I showed you just basically when you share it, you select this option to share the video. Audio.
Okay, I think because I stopped sharing and I shared again, I must have missed selecting that option. But let's try it now.
If you want to do that, we have a few minutes.
All right.
In the meantime, if anybody has any questions,
sorry, go ahead.
Go ahead and you can play the video. In the meantime, you can play the video. In the meantime, it has to share him.
The route-operable unmanned navigation of drones, or rounds, will allow the autonomous operation of drones in known environments. Rounds was developed by the Department of Energy Light Water Reactor Sustainability Program to help automate activities at the current fleet of U.S. nuclear power plants. Cost and safety concerns have motivated the program to search for alternatives to plant workers performing routine activities, such as monitoring equipment or collecting readings. Rounds allows a drone to automate these manual processes, collect the same information at a much higher frequency, and reduce human exposure to hazards. Industrial environments often have obstacles that can be navigated by drones, only if they are equipped with the means to quickly recognize and react to the environment. Other technologies that rely on environmental mapping are not as fast and precise as rounds. They are also more expensive and require additional sensors, which add weight and consume more power. Rounds enables a drone to autonomously, accurately, and quickly navigate its environment and return to its charging location within a known area, covering a long route on a drone's limited battery charge and preventing the need for charging stops along the drone's flight path. The novelty of this technology lies in Round's use of artificial intelligence and advanced image processing to frame the QR codes in a video stream and use the frame shape to reverse calculate the drone position. Rounds can then tightly control the drone's motion through high-performance controllers, such as those used to control missiles and satellites. By leveraging the drone camera and printed QR code stickers, the cost to deploy Rounds remains low. Rounds can be used in industries that perform security and operations rounds, warehouse surveys, and chemical or radiation monitoring in hazardous areas, among others. For further information, please contact...
Hi. It's more of a, I already kind of mentioned everything in the video. It's meant to play the video before I talk about in details, but it's all good.
No, thank you. Thank you so much. Thank you so much.
Hey, Walter, I think JP had a question.
Go ahead.
Yeah, Dr. Rashtan, good presentation.
Thank you.
For
can-
some reason,
can-
I hear a feedback.
Yeah, there's a lot of feedback.
Doctor,
There's a
stop
lot
sharing
of
the screen.
feedback.
Doctor, stop sharing the screen so that way there.
Yeah, that should be better. That should be better.
So, Dr. Rashtan, good presentation. I like to know more about the automation of fire, inventory, and gadgets. Something that caught my attention is one of the slides was about the process and anomaly.
JP, you got muted for some reason. We lost you for a bit.
I was talking to myself.
So well, I heard the process anomaly and then I lost you.
Yeah, so one of your slides is about the mechanical failure and sensors as well, mechanical and sensor. Can you expand on that? I understand when it's mechanical, it may take time for the data to understand that, hey, something is going to fail. But when it's a sensor, why take it so long? I mean, it should be right away. Can you expand on that?
Yeah, because sensor failures are it's a very good valid point, JP. So some sensor failures, or most of the sensor failures we see in the nuclear power plants are related to drifting. And what that means is the sensor is gradually, the performance of the sensor is gradually changing in time, but it's really slowly. That is one of the reasons this happens in nuclear power plants is radiation. So radiation causes the sensor physics to change in time, but it goes really slowly and it takes months to even appear. So in that case, the one I showed you, it wasn't that slow. It was relatively fast, but it didn't happen instantly. It just started drifting to the point where it failed. And the moment it drifted, that's where you want to catch it before it actually goes into. I mean, so in some cases, some sensors are not critical and you can wait till they fail. In others, if they're drifting, you want to know that they're drifting ahead of time.
Yeah, that's the one that I do have concern. I'd rather like to be changing a bulb if it's needed. I know that hypothetical, if we compare with a pharmaceutical, they have like, let's say a toothpaste production, they have line 1, line 2, line 3. There is a person who have all the log of each part and when they're planning to failure. So they change all of those before failure. So I'm assuming that, I mean, that's the similar of what we do in the power plant. So thank you for explaining that you're referring, I mean, for the drifting on the 2 days.
Yeah, and for the equipment, to your point, JP, it's everything you have, even your vehicle has equipment that would fail in time. They all have a life into them, right? Yep. Now, the challenge is finding what matters most and then monitoring these and determining what is the remaining life of that equipment to be able to decide when you want to change it. Because if you the conservative approach, and actually the industry has been doing this now, they tend to change things on a periodic time, so periodic manner. So they say this equipment, we expect this to last for 10 years, and then at 10 years we have to change it. But in reality, this equipment might last for 20 or 30. So when you change it in 10, you're actually wasting money. So now they went from preventive maintenance to predictive maintenance, which is instead of just we prevent the failure, we just change it regardless. No, we have to predict if it's going to fail and then change it if we need to, because that saves us a lot of money.
Yep.
Hey, Hamad, a great presentation. Thank you for participating in Tech Talks. I had a quick question. Obviously, a lot of the research is targeting commercial nuclear, but some of those applications or technology have direct application to DOE EM and their decommissioning mission. So is there Idaho or other national labs working in similar technologies to be applied to the decommissioning side of the house? Because I see direct application of the fire, detection, for facilities that are sitting there, call in dark, or some of the other facilities that are operational. That the reading the gauges would also save money and time. So do you see any transition from the commercial nuclear into the DOE EM side?
Very good question. So the short answer is yes. And the way we operate usually is I work for this Light Water Reactor Sustainability program. So the focus is the current fleet, right? But I very closely work with folks that are working in different programs within INL and outside INL. So we get exposed to what they're doing, and they get exposed to what we're doing. And very often I get calls from people that they want to leverage this technology for a certain application. For example, the drone technology I just showed you. Very recently, we got approached by people who are working on the safeguard side, and they said, "Well, you know what? We can replace, instead of people guards going now and inspecting spent fuel pins, we can maybe have the drone fly around and do this, and let's work on this." So that does happen. Our means of facilitating this is the events, conferences, and events where we present things and we share what we're doing with others. But it does happen.
Thank you very much. Great presentation.
Yeah. On that note, well, thank you, Dr. Razat. Anybody has any more questions before I?
So this is Himanshu. So one question I had regarding, I think you mentioned 16 models, and then it was combined to find the solution here. So are you referring to 16 different architectures, or it is one model with 16 layers actually?
Oh, it is 16 different architectures. There are different architectures in different papers. So we did a literature review. We found people who have used different architectures of models for the same problem, and we tested them all, and then we built an ensemble of the best of them.
Okay, so you said so how did you combine those different architectures to form the ensemble?
So that's the part where I can show you what we did exactly. There are multiple ways we can do this. We can I'm just going to give you a short answer, but I would be happy to discuss this further with you, Himanshu, if you want.
Okay, sure.
So you can always add a weighted. One approach we did is we had a weighted approach to each the decision from each model, and based on how they performed, and that the weight was based on how they performed. That's kind of the simpler way of doing it. Another was the voting approach that we can use for these models, but this is still, I mean, these approaches are what we have so far. And we already are more than 99% accurate. We're still trying to figure out what is the best way to combine them.
All right, thank you. And thanks for the excellent presentation and showing so many different applications of AI, ML in nuclear industry. And as Leo mentioned, definitely a lot of EM applications also can take advantage of all these technologies that are being developed at your location. Thank you. Thanks for the excellent presentation once again.
Thank you, Dr. Rashan. Just to remind you that this is sponsored by the Department of Energy, and the whole purpose of it, the platform of these Tech Talks is, again, what you mentioned, is exposure to what you're doing to other scientists and subject matter experts. And anybody has any additional questions?
Yes, this is John Moon from DOE EM. So this is more of application. Let's say you use the drone for security aspects of it, going around the perimeter, and let's assume there is someone who has cut through the fence and they're wearing camouflage. And I don't mean it in any disrespect or anything like that. I'm just assuming with AI, how would you look at the image from, let's say, the background of forestry compared to someone who's wearing camouflage? Because, from the videos, it may look very similar, But with AI, I would think that you could kind of look at the differences.
Yeah, so I'll answer this even though so my focus has been more on the enabling the drones to navigate indoors, right? Because that was a challenge for us. We couldn't fly them indoors in the first place autonomously. But the problem you just mentioned is very similar to the smoke problem we had. So you have things that should look like their background, but they are, in this case, for example, a soldier or an intruder who's wearing camouflage and comes in. That's where you start looking at the temporal effects. So you, instead of just looking at a frame and trying to classify if that person is actually a person or just a tree, now you see the motion, the difference between the different frames is gonna highlight that this is something has changed in that environment. So you can look at if you look at the multiple frames, and you'll see that specific tree, or I mean person looking like a tree, is actually moved somewhere else. That's something that you should flag. And we use the same thing we're using the same thing with the smoke, because smoke sometimes look like mist, but mist is more steady. Smoke moves faster. So motion is another factor that you can consider as a feature that can help you catch something like that.
Yeah, I was wondering if you would have to use some other methodology, like let's say infrared or some other technology, or would you be able to capture the differences and AI would be able to differentiate the small changes, whereas our eyes could not, because we're distracted so much.
You're right. You're right. I mean, I also mentioned that with the fire, that at the end, if we want to really reach something that gives us almost a zero false positives or false alarms, we'll have to combine different sensors. We'll have to look at smoke detectors, for example, in that case, or infrared cameras also. It's just that specifically, but just look, the AI part would be more useful on the optical side. Now, the other sensors are going to reinforce your decision on whether this is a fire or an intruder or not. But the AI part in that is going to be more into the sensor fusion. How do we build a decision tree, for example, that would get all this information and make an informed decision based on them? But it's a valid point, and it's a tricky application to tackle. And I think we're facing something like that with the smoke, as I mentioned. It's not as easy as catching fire.
Yeah. Thank you very much.
Thank you.
All right, guys. Thank you so much for the interaction. I appreciate all those questions. Just a reminder as we close, the presentation slides will be available at the dndkmit.org Tech Talk link, which was provided in the chat. There's also a feedback form in the chat link that I appreciate if people fill it out. It will give us a good indication of the future topics and the interest in the community. And I just open the floor one more last time to see if anybody has any other questions, comments. Any closing thoughts from the DOE? We have some folks from DOE that they're sponsoring this Tech Talk. Any thoughts?
This is Jennifer McCloskey. Thank you so much for walking us through it, for the videos, for the presentation. We are grateful for the opportunity to learn from you. Thank you so much.
Thank you for hosting me. I appreciate it.
I agree.
Walter, we need to mention about next talk by Larry Boyd.
Yes, we are talking to Oregon National Lab. Larry Boyd, actually, I think he might still be on. I'm not sure if he's still on. He's probably going to be presenting our next topic from Oregon National Lab, and then we haven't nailed down the exact title of the presentation, so we'll be sharing that on the Tech Talk website as well shortly. Once again, thank you so much, Dr. Razan, for your presentation. Very informative. Thank you for your time. Thank you for those who attended. Thank you for your support, and we'll meet you next time.
Thank you, Emma. Thanks a lot.
Thank you. Bye.
Bye.
Thanks again.